All right, guys. Um, so let's finish up our discussion here of steady state enzyme uh, uh, mechanisms with the consideration of so-called bisubstrate reactions. Now, the Michaelis-Menten mechanism that we've been talking about, which is sort of a single substrate enzyme conversion of product, is by no means uncommon in biochemistry, but it's also by no means the most common mechanism. It's at least as common, if probably not more common, to have reactions where two things have to come together on the surface of an enzyme in order for a reaction, a critical reaction, to proceed. These are, as I've sort of indicated here, are so-called bisubstrate reactions, right? And you've already seen some examples, right? I introduced one to you, hexokinase, sort of this reaction I keep coming back to over and over again, which the two substrates would be, of course, glucose and ATP. And you've seen another one just recently in the case of chymotrypsin. You may not have realized that was a bisubstrate reaction, but it is, right? So first substrate is, of course, the polypeptide, but the second substrate is, of course, water, right? So to resolve the acyl enzyme intermediate, that tetrahedral intermediate, the acyl enzyme intermediate, I should say, you have to bring in a molecule of water, remember, after the amino terminal side of the peptide's been released, in order to release the second half of polypeptide, right? So that's another example of a bisubstrate reaction. Now, the manner in which two substrates are engaged by an enzyme can happen in several different ways. And there's sort of three big general ways in which this tends to happen, and there are sub-variations. We're just going to talk about the three big types. And in some situations, the steady state kinetic behavior of these different reactions can give you clues to the underlying behavior. Really, in only one case, is the steady state kinetic behavior pretty diagnostic of the underlying mechanism. And I'll mention that in a second. But in general, what we're going to do is just sort of talk about these at sort of a very high level. It's possible, of course, to take the descriptions, the schemes that we're going to talk about, and derive from them more detailed steady state kinetic equations. But again, at under the initial rate assumptions in large substrate excess, these systems are still going to behave very much in the way we've discussed as steady state type or Michaelis-Menten type enzymatic reactions. And it's as you vary the different substrates relative to each other, you can sometimes get useful information. Okay, so the first type of mechanism is, the one we're gonna just sort of talk about here a little bit, is of course the so-called random sequential mechanism. And random should give you a clue as to what's going to be going on here. So in this case, one would have an enzyme, let's say E, right, that needs to bind two different substrate molecules in order for a reaction to happen, right? And this can happen either by binding substrate A first, or it can happen by binding substrate B first to form an EA Michaelis complex or an EB Michaelis complex. But remember, the reaction this enzyme needs to run requires both. So we're not done yet, right? So the full Michaelis complex hasn't been formed yet. And in this case, the EA complex would then bind a molecule of B. In the case of the EB complex, it would then bind a molecule of A to form this so-called EAB ternary complex, right? So this ternary complex between the enzyme and both substrates. This would then go on to either, say, in the case of a group transfer reaction, would be, say, E, P, and Q, or in the case of a condensation reaction, it might just be like EP, right? Which would then decay to E plus P. In the case of, say, a group transfer reaction, again, we now have to let go. There are two products. We now have to let them both go. And this could, in general, for enzymes like this that follow this mechanism, you could go either way. You could release P first, form this sort of EQ complex, and then let go of Q, right? Or you could go the other way, in which case you would let go of Q first, form the EP complex, before then letting go of P to then regenerate the enzyme. Okay, so the important things here, the big things to remember for a bisubstrate enzyme that's following a random sequential mechanism is that the particular path the enzyme takes to get to this ternary complex doesn't matter. It could bind A first, then B just doesn't care. But the ternary complex, having both substrate molecules on the enzyme, absolutely has to happen. They both have to be there at the same time for the reaction to proceed, right? So they're, the key thing here again is that the specific pathway of assembling the Michaelis complex isn't enforced. Either way works. Okay. All right. So if you have the random sequential mechanism, you can imagine sort of an alternative to this, right? Which would be the so-called ordered sequential mechanism, right? So that would be another way in which enzymes can do this. All right. This one's not so hard to conceptualize. In this case, we would, of course, have our enzyme that binds substrate A. Again, it's a bisubstrate reaction, so we got something else to form. So we form this initial sort of pre-Michaelis complex, the binary complex E sub A. But now we then have to bind the second substrate molecule B to form our true EAB ternary complex here. Right, there we are again. Right, and now chemistry can happen. And again, in the case of, say, a condensation reaction, we would just end up with, EP, or we can end up with a reaction in which we did like a group transfer, E plus Q, and usually for enzymes that are going to do this, like a group transfer, if it's an ordered sequential going in, it's ordered sequential coming back out. Though again, I'm never going to say never because I'm sure there are exceptions to this. So you have P, EQ, right? Q and then E, right? Okay. So the big ideas here again are that in this case, unlike with the random sequential mechanism where the path to that ternary complex didn't matter, for the ordered sequential mechanism, there's only one path, right? A must go on first, then B must go on. As with the random sequential, the ternary complex is again required. Both substrates have to be on the enzyme at the same time. That ternary complex is obligate. And now in this case, the order in which the substrates go on is also obligate. In fact, in many cases where an ordered sequential mechanism is used, the binding site for the second substrate, right? This binding site doesn't even exist on the enzyme until the first substrate is bound, right? So that in the absence of the first substrate, the B part of the active site isn't ordered or isn't structured, or binding determinants are essential from A. You can't bind the B substrate at all. And this is often a mechanism used where B is an expensive molecule. It's something that took some investment to make, or took some investment to scavenge from the environment. It's something that the cell really doesn't want to waste. So that if it bound, and remember, you're going to go through the transition state. We're going to activate this guy. We're going to do something with it. If the enzyme made a mistake, right? So it just like hydrolyzed something, right? Like a high energy phosphate bond, that would be super energetically expensive. So one of the ways evolution has encoded quality control in this to prevent that from happening is evolving the enzyme so that you can't even bind B until A is already on the enzyme, right? Dehydrogenase and reductase enzymes. This is a really common way to build those enzymes, and the way in which they use reducing equivalents in NADH, NADPH in order to keep them from being wasted. Okay, the final example, again, just in general terms that we're going to think about in terms of mechanisms. The final big picture bisubstrate type of reaction is the so-called double displacement, or also more colloquially known as the ping pong mechanism, right? And this one, again, requires two substrates, but it works in a very particular way. In this case, we'd have enzyme plus our first substrate to form enzyme A Michaelis complex, which then does some chemistry, right? Frequently, this is going to involve a covalent intermediate with the enzyme, but it doesn't have to, right? You can sometimes just have something very tightly bound, right? But frequently, this will involve forming some kind of a covalent intermediate with either the enzyme itself or with a prosthetic group that's on the enzyme, right? And then we would release our first product, right? Now, we then have enzyme. I'm gonna draw this a slightly different way. Let me make this like P, like that little bar, right? EP now plus B. And so we have this EP B complex, right? Which now does some chemistry of some kind to regenerate the enzyme. And in the case of, say, a group transfer reaction, maybe this would be, PB, or maybe this would make something completely new, like R or something, right? Okay, so notice something about the ping pong mechanism, this double displacement mechanism. Something's missing compared to the last two. There's no ternary complex. So the double displacement or ping pong mechanism, you never form a ternary complex. It's a pair of sequential reactions. The enzyme first interacts with and does chemistry with the first substrate, sometimes releasing a partial product. And only once that's over can the enzyme now bind the second substrate molecule and complete the reaction. Therefore, ping, then pong, right? Okay. Now, one of the reasons, this is a common mechanism. In fact, you just saw one, right? Chymotrypsin. Looks kind of familiar, right? Where this first reaction here, that would be the first step up through cleavage, right? And release of the amino terminal part of the peptide. And this would be, of course, binding of water and hydrolysis to release the C-term part, right? Ping, then pong. Okay. Now, one of the reasons this is ping pong mechanisms are one of, or maybe the one bisubstrate, more complex sort of reaction where steady state enzyme kinetics can actually be pretty diagnostic, right? And useful. For a lot of the other mechanisms, variations of the ordered sequential and the random sequential, steady state kinetics is of somewhat limited utility in figuring out what's really going on. But in the case of the ping pong mechanism, the steady state kinetic behavior of these systems can actually be kind of diagnostic that you have a ping pong mechanism going on. So where this is often or frequently illustrated is with respect to these linear transforms, specifically the Lineweaver-Burke plot, where one, remember, if one had 1 over the concentration of substrate versus 1 over, on this axis, 1 over the initial rate, remember it's double reciprocal plot, what you find is if you do a series of steady state experiments, right? So when say this is 1 over substrate, maybe even a little more specific, 1 over the concentration of A, because remember, it's bisubstrate, so we got to vary two things. We got to vary them under steady state conditions and look at the initial rate. So what you would do is you would pick a concentration of, say, B, and then vary the concentration of A. And of course, if you're under good steady state conditions, you get nice initial rate behavior. And in the double reciprocal plot, you would get a nice straight line, if I can keep my pen from erasing things, right? Just remember that, right? But now the cool thing is if you actually do have a double displacement mechanism, you now change the B concentration and these curves shift in a characteristic way. Specifically, the way they shift is they remain parallel to each other and they shift in this direction, right? So that as the concentration of B increases, you get this family of parallel curves that is pretty diagnostic of a so-called ping pong or double displacement mechanism. Okay, now that's an example of a situation where steady state kinetics is really helpful in understanding how an enzyme, the underlying mechanism of an enzyme. But normally what you'd use is some combination of steady state kinetics and then so-called pre-steady state kinetics, where you no longer presume you're in large substrate excess, right? And necessarily following initial rate behavior, and you use the temporal behavior of that, the production of product, as you varied the what you think are the different substrates, often then in combination with structural biology, mass spectrometry, kinetic isotope effects, all these other tools that you would then use to really take an enzymatic mechanism apart. Steady state kinetics, good thing to know, remember, is sort of the first step in characterizing an enzyme. It's rarely the end point. It almost always requires more than that. Okay.